residue theorem according to Cauchy. Following Cauchy, see the next equation. Using Green's theorem, further details when we get to vector calculus. See the next equation. We get, see the next equation. And substituting the Cauchy-Riemann relations we get, see the next equation. When f is analytic in the region R, and the function derivative is continuous there, needed to use Green's theorem, then the above equation holds. Later Goursat was able to show that the condition on the function derivative to be continuous is not needed. It is only required that the function be analytic interior to and on the boundary curve. From the above we can see that the integral of complex function on a closed contour will equal the sum of contributions from 1 divided by z, terms only the residues each with a factor of 2 pi I.
Equation 2-5. 2.3 Complex structure, field phenomenology, thermodynamics/analyticity. We saw the concept of complex structure mentioned in section 2.1, and how adding complex structure to a real function leads to a complex function, described in section 2.2. Let's now formally define this construct. Complex structure. A complex structure can be defined on a real vector space by adding the linear transformation j:v vector v such that j squared equals -1. Note that complex structures only exist in spaces of even dimension since they entail a doubling of the dimensionality. Use of complex scalars can then easily be absorbed into a vector space with complex structure and be replaced with a real scalar. Equation 2-6.
The quantum theory, Book 4, will have a sum on terms of the form e raised to the iet power. Now suppose the time dimension variable is endowed with complex structure and Wick rotate, to have the substitution t equals I divided by kt, we then have a sum on terms of the form e raised to the negative e divided by kt power, which is the classic form for the partition function of the theory. If it is the theory of an equilibrium system, then the partition function generates all of the thermodynamics properties of the system using standard methods, covered in Book 6. In Book 7 we will see that we need not posit the addition of such a complex structure as it is already present from the emanation process. 2.4 Field algebras and Cayley algebras. Field algebras and Cayley algebras can lose nice properties that we take for granted with the real and complex numbers such as associativity. Recall that associative means that there isn't order dependence in computing ABC, A, BC, sadface ob, C, etc. As we go from real numbers to complex functions, aside from a trickier multiplication process, there hasn't been an order dependency on operations. As we generalize to hypercomplex, Cayley algebra, numbers or to quantum numbers, various forms of order dependency begin to occur. Associativity is lost for Cayley algebras after the complex numbers, for example, but some partial associativity is still retained, alternativity.
Often when working with numbers, algebras, and operators, in quantum mechanics, it is useful to distinguish between C numbers, classic numbers, with associativity, and Q numbers, quantum numbers, often represented by a matrix. Using this terminology helps to clarify how different formations are possible, and equivalent, but with and without use of Q numbers. When considering the quantum version of a classical system, e.g., quantizing the system, there is a standard process whereby C numbers become Q numbers, where the canonical commutator becomes non-zero, now having a magnitude Planck's constant in some systems. A less well-known process is available by way of a path integral formulation where there is no need to introduce Q numbers, per se, but there is still a need for use of Grassmannian algebras when describing fermionic, and tight commutative, matter. By use of some conventions over structured paths, it is even possible to eliminate all non-simple algebras in the path integral formulation, no need for Grassmannians. 2.5 Dynamic field with finite propagation. For the static fields considered in Book 1, the matter of finite field propagation wasn't relevant. Once we allow field changes to occur, the question naturally arises as to how fast those field changes propagate. For many situations, relative to the motions in the system, those speeds can be approximated as instantaneous. But for many other simple systems, it is easy to see the inertial properties of matter entering into the system to give finite propagation. One of the easiest ways to consider such systems is to take a masses connect by strings in a line and to take the continuum limit. as this is turned into a 1D string. To address this, let's consider some classic problems from Fetter and Waleka.
Example 2.1, Fetter 4.12. Consider a linear chain of 2n masses, with springs alternating, connected to a wall by a spring at each end. Let the masses be the same, m, and the separations the same, a, but have alternating spring constants, k sub 1 and k sub 2. A. Find the dispersion relation. Examine limiting cases. B. Apply periodic boundary conditions and find the allowed frequencies.
Solution. A. The equations of motion for each mass depend on whether it is at index position, that is even or odd, where it is assumed that indexing is from the leftmost mass and the leftmost spring has spring constant k sub 1, and the jth mass displacement is given by eta sub j. See the next equation. And see the next equation. Using eta sub j equals alpha e raised to the negative I omega t power exp of iqaj is used for j times even, and eta sub j equals beta e raised to the negative I omega t power exp of iqaj is used for j times odd.
See the following group of equations. These two equations can then be solved to obtain. See the next equation. For k sub 1 goes to 0, the system degenerates to masses separated by spring k sub 2. Omega squared equals the fraction with numerator 2k sub 2 and denominator m or 0. For k sub 1 equals k sub 2. Omega squared equals 2k over m times 1 plus cosine qa equals 4k over m the sine squared of qa over 2 period.
Example 2.2, Fetter 4.16. Let's now consider a 2D version of the previous problem, but instead of springs let's have masses fixed on strings under tension, the strings forming a 2D grid, the masses at the intersections. Suppose F equals K for springs is carried over to string under tension tau, then trivial that K equals tau divided by A, and we have. See the next equation. Where the mass displacements at grid position, I, J, is 0 at the boundaries, mu sub 0, j equals 0 equals mu sub n plus 1, j, etc. The equations of motion are. See the next equation.
See the next equation. To calculate the dispersion relation, let's use the form of solution. See the next equation. We can then obtain. See the next equation. Let's take the limit of a continuous mass distribution. See the next equation. And see the following group of equations. Thus, see the next equation. Note that the dispersion relation for the discrete case is anisotropic in the xy plane, whereas that for the continuum is isotropic. Exact normal mode frequencies occur, n is less than infinity, at see the next equation, where see the next equation, for the continuous system as a check, from L equals TV.
See the next equation, for which the Euler-Lagrange equations give. See the next equation. In agreement. Thus, in continuum limit, the differences can be related to differences in a scalar field. See the next equation. And the kinetic terms have. See the next equation.